You can complete example 4.3-1. It says heat flow through an insulating wall of a cold room. So a cold storage room is constructed of an inner layer of 12.7 mm of pine. Okay, so the first layer is made of pine, a middle layer of 10.6 mm of corkboard, and an outer layer of 76.2 mm of concrete. So the wall surface temperature is 255.4 Kelvin and 297.1 Kelvin at the outside surface of the concrete. Now, we are asked to use the conductivities of, in appendix A.3, we are asked to calculate the heat loss in watts for 1 meter squared of area and the temperature at the interface between the wood and the corkboard. So allow me first to sketch a rough illustration for this. Okay, we have this sketch like of the wall. Our wall is made of 3 layers. Okay, in this approach, A will be the, okay, this is made of the pine. Okay, that's the pine. The B will be the middle layer. It's made of the corkboard, and the next sticker to it, this one, letter C, it's actually the concrete. Okay, like this is the surrounding, and this is the cold room here. So this is the cold part of the section. This is the surrounding, which is quite at a higher temperature here. And of course here we are given some temperature. The temperature here of the outer wall, this one, okay, like this is of temperature like TO. TO is equal to 297.1 Kelvin. Okay, that's the temperature of the outside of the of this one, of the surround, like the wall, the concrete wall. And the temperature of the cold room, this one, the temperature of this pine here in the cold room is actually the TO, the cold room temperature, or the wall next to the this one, the surface of the pine. So like if we can see it, like in there, like TI will have a temperature of 255. It's quite a cold temperature. Anyway, that's why it's called a cold room. And of course, we know that heat will then flow from the higher temperature to the lower temperature from the surrounding. This wall is at higher temp, the inner wall is at lower temp, so heat will flow from right to left. So heat will flow from, okay, this wall to the outer wall, so it will leave through there. Okay, so it will leave through the heat will enter the cold room. Okay, so this series of insulator actually has a certain values of their thickness and their conductivities. Okay, so we have rewritten here the different, thickness of the different sections. In this case, the thickest part is the corkboard. The main insulator, as you can see, it has the lowest heat conductivity. It's 0.04. Well, the concrete, it's quite the highest, but the concrete must be there because if there's no concrete, then the corkboard is very fragile and it could be easily scratched if exposed to the surroundings. Okay, that's why we have the concrete here protecting that corkboard, and also that pine, it must be sturdy enough, and corkboard cannot be exposed to a harsh environment, and the pine will actually also maybe give it a good look in the inside of the cold room. Now, well, we have this, and we're being asked to calculate for the heat loss, still heat loss, and we're looking for heat loss. We have a very simple equation to use. It's simply, if we're looking for heat loss, simply the equation will be Q is equal to the driving force. What drives the flow? Difference in temp over the what? The resistance R. The temperature here is that the temperature in the surrounding is quite high, 297.1, and in the inside of the cold room it's quite low. That's why we'll expect a heat flow from the surrounding to the cold room. And delta T is easy to solve. How about the R, the resistance? Well, the resistance supposed to be given by the equation R is equal to, it's inversely proportional to the conductivity, also with the area, and just directly proportional to the thickness delta x. Now, since we have here resistance in series, just like electrical resistance, when they are in series, it's easy. Like because we have here the resistance of this, the resistance of this, and the resistance of this one, of these boards, different resistances. Simply, the total resistance is just lumping that. You can simply add that. Our total, if we know from our electricity or electric circuits or the basics that we have, well, we simply, the resistance total or total resistance is the sum of these resistances. Okay? So with this information now, one can compute for RA resistance for the pine, resistance for the corkboard, and the resistance for the concrete. By simply delta x, we already know delta x, the thickness, K, the conductivity for that particular material, A, the area. In this case, area is supposed to be, we're calculating per what? Per 1 square meter. So area is simply 1 square meter. So with that, we then have the following values in terms of Kelvin per watts. Now, to get the total resistance, we simply add them together, right? But wait, I think I made a mistake really in calculating for RB. Supposed to be RB, the resistance of RB will not be 0.0433 but 2, this is KB only. It must supposed to be 2.346, okay? 2.346. As you can see, RB offers, the corkboard offers the highest resistance among the three resistance. The sum of them will be 2.5301, and the unit of course will be Kelvin per watts. Now if we substitute that here, we can then compute for Q, right? Delta T is just simply 297.1 minus 255.4. So 297.1 divided by the total resistance, 25301 Kelvin per watts. And if we evaluate that, that will then lead to 16.48 watts, meaning every square meter of area, every square meter of that, perhaps if that is a 1 square meter, 16.48 watts of heat is escaping through that, or actually is passing through that. And that means that it will mean a heavy load, a load to your refrigeration system, so that you could be able to remove that heat back in your cold room. But I think we only have answered the first question that asks us for how much heat is lost. We're also being asked, what is the temperature at the interface between the wood and the corkboard? So this is the wood, the pine wood is here, and the corkboard. So we're being asked, what is this temperature here? Well, to solve for that, allow me to drag it first. There are a lot of ways to do that. So let me label that temperature here like TAB. Like let me call that TAB, the temperature, okay, TAB in between A and B. Now, if you'll be asked which is higher, TAB or TI, then of course you will say, well, TAB must be higher than TI because heat will flow from right to left, meaning this must have higher temp. And actually, since heat is passing through this resistance in series, the same amount of heat is passing through this concrete, passing through this corkboard, passing through this pine wood. Okay, same amount of heat. Looking only on this pine wood, since this pine wood will have the other surface will have a temperature of TAB, and the other surface of the pine wood will have a temperature of TI, we can use this equation strictly only for the pine wood. Like Q of the pine wood that passes through that pine wood is just equal to what? Delta T over R. But this one, this delta T, will only be, what will be delta T within the pine wood? Now, what is Q? Well, Q will still be the same, right? Q will still be the same for that, since the same Q is flowing through these three resistances. So we have 16.48 watts. And then Question is, what is the difference between the temperature? What is the driving force within that pine wood? Well, the temperature that drives the flow will be TAB minus TI because the other end of the other surface of the pine wood is at TAB, that's higher temp. Then the other surface is exposed at Ti, that's Ti, and Ti we know Ti, right? Ti is supposed to be 255.4 Kelvin. So by this, simply using this equation, only for the pine, or in this case A, section A, divided by the resistance. We know the resistance of a pine wood, right? This is already known. This one, 0.0841. Okay? That's Kelvin per watts. Okay? And therefore, in this case now, the watts and the watts will cancel, and working with manipulating this one, we'll then be getting TAB, the temperature at the interface or between the wood, the pine, and the corkboard will be 256.8 Kelvin or 0.79 Kelvin. So TAB from this one, TAB will be equal to 256. Wait, I will not put that there. TAB then will be equal to 256.79 Kelvin, meaning that's a temperature here at the interface. So you can see the temperature is dropping. Here at the outer surface is 297, then it drops, then it drops, and it drops. Then delta T can actually be computed using just this simple approach. I hope that you find this video helpful, if not making you um, having more problem with this, with the approach in the book. But I hope that uh, these videos makes the problem more interesting. Thank you.